So I'll be introducing 7-dimensional telescope for multi-messenger astronomy and actually many other science cases. And we'll talk a little bit about the status and also what has been done and what will be done, and also the our other observational efforts that to find electromagnetic counterparts during O4 run. Okay. So everybody knows that we are now exploring the universe with something other than the light. So it used to be that we use only electromagnetic wave. People expanded to multi-wavelength electromagnetic wave. But now that we have really new ways to explore the universe, like gravitational wave and neutrinos. And what the focus right now here is about the gravitational wave. So from 2015, that many gravitational wave detections have been reported, but up to until now, the most detections, almost not all, are black hole mergers, which are supposed to not emit any electromagnetic signatures. So with only gravitational wave signals, it is difficult to localize their location, which means also that it is difficult to use them for other multi-messenger astronomy and other astrophysical applications. Right? So the good hope is that if you have neutron star neutrons merger or neutron star black hole mergers, they can produce detectable electromagnetic signals such as GRB signal or kilonova. So this happened in 2017, August 17, and many people actually looked at this event. More than 3,000 people studied this event intensively, and many interesting papers came out. And the hope was very high at the time that we will be doing this again and again in the next years. But interestingly, this has remained the only GW event with EM counterpart identification so far. So what's going on? So there are multiple difficulties. Of course, maybe the rate for BNS merger is not still very well known. But first of all, even if such events exist, the search area, the localization error is very, very wide, meaning that typically you need to search more than 100 square degree, often thousands of square degree. And it's a really difficult effort to do so. Also, kilonova are kind of relatively faint transient compared to supernova. At its peak luminosity, it's more than 10 times fainter, meaning that, and also it decays very fast, like in this figure, right? These are typical supernova light curve, and the kilonova becomes very bright and then decays very fast. So you need to find them very quickly. Otherwise, you may not be able to identify them. Also, if you start looking at many thousand square degree area, then you will find many other transients and also bogus signals that could be confused with the kilonova. So those present difficulties for finding kilonova associated with the gravitational wave events. So what we have done is to establish a network of telescopes around the world called GW-EM counterpart Korean Observatory, and in short we call it GECKO. So at least we can cover any time zone by establishing a telescope network. And what I'm going to talk more about today is this new facility that we have established in Chile called the 7-dimensional telescope. So search for kilonova is processed in this way. So with the GW alert, you have this kind of localization area map, and then you use your telescope to cover this wide localization area. And each point here represents each telescope pointing, and each of these typically is made of this kind of images. In this case, this is a KMT-net image representing 2 by 2 square degree. And within this image, there are a few 100,000 sources there. You will need to find new sources in this image, and which takes a lot of time, of course. And then you find them. You find many, many candidates. And then you take a spectrum to make sure that this kind of resemble, kilonova spectrum, not those new known supernova or other transient spectrum. And then you do follow-up observations to better understand their characteristics later on. So there are multiple steps for this search process. So what we are trying to do is to kind of remove some of the steps for the search. So what we want to do is to do imaging observation and then spectroscopic observation simultaneously to remove the mid step to expedite the transient search. So our aim is basically you do wide area search, you take spectrum in each pixel, and you do this kind of observation in time series. So a new way to explore the universe in a kind of new way. So basically, we take this kind of image in series, and each kind of this circular region shows that we get a spectrum at each point. And then we can do this kind of observation in time series. So to do this, we developed 7-dimensional telescope, 7DT. This is still our final plan is to have 20.5 meter wide field telescopes. We are building this in Chile, and then with this telescope, you can do spectral mapping of the sky. Pixel scale will be about 0.5 arcsecond, and it can cover 1.25 square degree in a spectroscopic mode. And if you want to do wide field mode, we can cover about 25 square degree at one shot. 7D means that, well, many of us probably knows what it means. I will ask X, Y, Z, that three-dimensional space, time, flux, wavelength, and radial velocity. So we are trying to explore the properties of objects in the universe in 7-dimensional parameter space. So telescope site is Chile El South Observatory. This is a privately owned observatory. It's not too far from CTIO or Cerro Pachon. And its altitude is 1,700 meter. And as in many other Chilean sites, it has many clear nights, and on average it's 320 clear nights, which is really good. Median seeing is not very excellent, but very good enough, 1.5 arcsecond on the ground layer for typical telescope, small telescope operations. And this site is operated by a company called Prof. So we help them to maintain our telescope and do also the installation of the telescope. Each telescope is like this, and the telescope is manufactured by Plane Wave Instruments in the United States. It has a 3-degree field size in diameter, and it employs kind of a high precision telescope mount, so we can do 5 minutes and 10 minutes tracking of the sky without guiding system. We use for the camera, we use a back illuminated CMOS camera produced by a Moravian company in GECKO. It's called C3 model, and it has about 10,000 pixels by about 6,000 pixels. So roughly speaking, it has 60 million pixels. Okay, pixel size is 3.76 micron, which is kind of smaller side for typical astronomical cameras, because our telescope has short focal length that you need to have a small pixel size to finely sample the sky. Okay, so this kind of produces 1.3 times 0.9 square degree. And with 20 such units, it comes out that total number of pixels is 1.2 gigapixels. So it's about 1/3 of the gigantic camera of the Rubin Observatory. It's not too very close, right? And the Rubin Observatory is a $500 million USD project. Our project is less than % of the budget. And I was actually, after the math, surprised at how many pixels we have. So the idea is that each telescope will have at least 2 medium band filters looking at different wavelengths. So we have 20 telescopes, so 2 times 20 means the 40 different wavelength elements can be sampled, and between 400 to 900 nanometer with a filter width of 25 nanometer, and each filter is kind of central wavelength is displaced by 12.5 nanometer, half of this filter width. So this is one filter, and another filter is like displaced like that. Okay, so that we can get about the spectral resolution 40-ish spectrum which is good enough for tracing the spectral shape of many transients. Okay. So basically, we are doing many medium band observation, imaging observation. We combine them together, then you get the spectrum at each pixel of the image. This shows the field of view of 7DT, roughly compared to the full moon size. So 7DT can fit in, 6 full moons can be fit into the one 7DT field of view, and then JWST NIR can also, field of view is like that. So we have a 1,000 times bigger field of view compared to the JWST typical camera. So with this kind of observation, basically you look at the universe and then you get spectrum at every place. And if there happens to be a transient here or kilonova, then you can trace the transient spectrum. And then if you do the time series observations, then you get the time series evolution of the this transient. 7DT can be operated in 3 different observing modes. Well, the third mode is just what I explained. You stare at the same part of the sky with all the telescope. You get spectral information at each pixel size. And then otherwise, if you want to do, then you can use the same filter. For example, broadband filter, R-band, stare at the same part of the sky. And then the 20 times 0.5 meter telescope makes the collecting area of about 2.3 wide field telescope. So you can use the telescope in that way. Or you can also have one single filter observation, each telescope pointing at different locations of the sky, and then you get 25 square degree coverage at once. Yeah. So current status, the Ji-hoon will update on this one, but briefly speaking, we have 15 telescopes have been installed, and 1 is being installed. And commissioning observations started with 10 units in October 2023, so about a year before that the test observation started. So this is the first slide image of 7DT, taking NGC image of NGC 253, and you can see that actually this is more like 1.3 degree, but see the wide field of view of this camera telescope. Oops, sorry. And this is like another image of a Helix Nebula taken with this 7DT. So this shows kind of the color images made with different wavelength images. So as you know, planetary nebula has many emission lines. So 7DT is good at sampling different kind of images. So you see here, you see different combinations of wavelengths used for constructing these color images. And actually, looking at different wavelengths, you see that colors of nebula changes dramatically. Right? So this is the power of, I think, that 7DT. So this is a zooming of the view, yeah. Different color combination again, and acknowledgements. All right. So next, move to the next. Okay. So current status again, we have 15 telescopes in place, and 1 will be added soon. Actually, we had another telescope operated on this site, different type, and we moved that to this site. So basically 17 telescopes are there. And 20 medium band filters are installed. We are doing daily observations with this telescope. And data transfer rate is currently 400 megabps, which is okay nowadays. We have established GPU type of computing server and also 1 petabyte data server. We are expanding that to 2 petabyte kind of level. Okay. And 7DS, I will expand that soon. Regular observation started in first half of the 2024. And we still have many things to do to improve the system. But anyway, the observations are ongoing. With this telescope, I mean, it's easy to distinguish typical transients such as supernova versus kilonova. And this gray spectrum shows a supernova spectrum, maybe about 1 month after the peak luminosity. And this is newly emerging kilonova spectrum, okay? And these red points and then horizontal bar represents basically the broadband filter observation simulation of these two objects. They are very, very similar in this broadband color. So it's difficult to distinguish again from the broadband alone. But if you have this, blue points, which are the 7DT data point simulation, and then it's very, very easy to distinguish two cases. Okay, so and then you can do other mock, tests to see how well, we can do identification. This is a little bit outdated. Probably Gregory will update this one a little bit more. So fitting example, for example, broadband observation with supernova and also kilonova, they look similar, but with the 7DT, then you have a very different appearance from the supernova spectrum. So anyway, let me just skip this. And classification like this has a very high accuracy compared to broadband, according to our early results. Okay, broadband, you could easily fail the identification, distinguishing the kilonova versus supernova. With 7DT, it's almost perfect. And then nowadays, we are also implementing AI-based classifiers to do fast classification. There should be many, many transients, so this is kind of necessary steps. So I will also explain the 7D sky survey. This is a sky survey we are going to do. Actually, we are doing right now with the 7DT. We will cover the southern hemisphere, entire southern hemisphere with this spectroscopic mode of the 7DT. So that survey is called reference imaging survey. The reason for the reference image means that we are going to do the transient search observation later on. So we need to have a spectroscopic mapped reference images. So that's why we call it RIS. And then we also have about 2-week cadence survey over about 1,000 square degree area, which we have not yet determined the field location, so that we can trace the spectral evolution of objects such as quasars and other kind of objects. And then for smaller region overlapping with the spheric deep field, we are going to do daily monitoring observation of such location. So basically, the reference imaging survey is going to have about 20,000 square degree coverage down to about 20 magnitude depths. And also the wide field survey, each epoch will have similar depths, but after stacking images for 5 years, for example, it can reach nearly 23 magnitude. And intensive monitoring survey, it will cover about 12 square degree area every day. And after 5 years, it can reach well beyond 24 magnitude. Okay. This is a current detection limits of the 7DS. So each RIS, and then planned detection limits of RIS, WFS, and IMS. And compared to all sky survey of Sphere X, this kind of matches very well. Actually, it goes deeper, but in terms of galaxy SED sampling, and it matches very well. Compared to the Sphere X deep field, then WFS and IMS has a good also sensitivity. Okay. So with this low resolution spectroscopic mapping, 7DT can trace spectra of galaxies and AGNs. This shows an example of a simulated spectrum. So red points are the simulated 7DS spectrum overlaid on a real spectrum of high band magnitude 18.3 magnitude quasar at redshift 0.822, and compared to the LSST kind of broadband observations here, then we can really sample these emission lines and continuum separately very well. So if we do kind of a time series monitoring of these objects, then it's easy to disentangle emission line variability from continuum variability, which will be useful for exploring the broad emission line region, and then possibly measure the black hole mass of the AGN, and then you could also possibly use it for the cosmological purposes. And since it has many 40 different bands, it could also do very well in photometric redshift front. So we have been doing a lot of simulations by our team, and also in collaboration with the Sphere X team, that so far this is kind of best prediction. So for brighter objects with enough signal to noise, you could do down to almost 0.2% accuracy in the photometric redshifts. For the fainter objects, then maybe 2% or so. But for most of the objects, maybe 1% or better. So this will have some good implication for providing galaxy catalog for future efforts of, for example, gravitational wave related to the cosmology. So 7DS galaxy map like this could be used for dark siren studies. So because we have very high accuracy galaxy redshifts, you can trace actually the clustering of galaxies along the redshift, on the line outside of the redshift. Usually the redshift distribution of galaxies are clustered together. So exception, and also these BBH or BNS mergers are likely to happen in massive galaxies. I think that with the highly accurate redshifts, then you can better constrain the cosmological parameters for sufficiently small localization areas of 10 or 20 square degrees. Okay. And then we can do many other studies, such as galaxy evolution, which is dependent on the environment, and also each galaxy can be broken into different parts, and then its spectrum at each part can be explored. So the environment study is also possible in this kind of level for the study of environmental kilonova or also supernova or many other kind of transients. Okay. This is also a kind of similar thing. So usually the galaxy surveys have been done over area avoiding the galactic plane. So because there are too many stars that could be confused with the galaxies or quasars. So this is one example that we did before. So we searched for quasars in the galactic plane area, behind the galactic plane to be exact. So this is a typical kind of higher galactic latitude field. Quasar can be identified with a color diagram or something like that. And this is like a low galactic latitude field. There are many stars. Our observation will take spectrum of every object here. Right? So it will be very easy to single out quasars or galaxies, so that to fill the gap in the zone of avoidance for galaxies and quasar surveys. So it will be useful for expanding the galaxy kind of survey, large-scale structure, tracing area to the almost entire sky. So 7DS research topics. We don't have much time. Actually, I've been progressing fast, so maybe we have enough time. But anyway, we don't have enough time to explain every topics. So I just explained the multi-messenger astronomy part. Okay, and actually we can do many interesting studies for AGN, like with the time series spectrum. You can do reverberation mapping of AGNs. Galaxy evolution, I just explained, with many redshifts, highly accurate redshifts and spatially resolved, SED fitting can be done. So many things can be done. Also, cosmology-wise, you can use multi-messenger astronomy part of the cosmological application too. Also, with the nice galaxy map, we can do large-scale structure, use large-scale structure to constrain cosmology. And also the AGN, you can use other tracers of the geometry of the universe to study the cosmology. Our galaxy, I think that looking at the Milky Way area, there are too many stars, but we don't worry too much about the confusion issue here, because that we can take spectra at each location. That I think that the 7DS will have a strong impact on this kind of stellar population studies of our galaxy. Also, there are many extended sources such as a planetary nebula that you show, also many star-forming regions. Extended objects in galaxies, our galaxy can be studied in more detail at each location with our data. And there are also other kind of transients other than the kilonova, like such as supernova, tidal disruption event, change in AGNs. Those can be studied very easily with the time series spectrum of the 7DS. And supernova lensing could be done, for example. And also, I think the solar system object is also a kind of interesting part. Solar system objects, it's always moving. So doing the spectroscopic observation is very, very time consuming. You cannot just point multiple object spectrograph at certain location, right? So, but with our, 7DT, then it's this, and within the 7DS there will be many moving objects in our solar system that will be sampled by our observations, and their spectrum can be studied. Okay. So one example, real data actually. Let me move on to real data. So this is one observation we did for a transient type 2 supernova called SN 2024 DIQ. This occurred in a galaxy at redshift 0.013, and we did time series observation of this supernova with 7DT. And 7DT spectrum is looking like this here and here. And this is a kind of the real spectrum taken by other telescope. And you can see that this has a kind of strong H-alpha emission line, interesting one. This is also kind of sampled. Then the rough shape of this supernova was sampled nicely with the 7DT. So it has so this is to demonstrate the power of this telescope for studying the spectrum of transients. This is another kind of observation for the asteroids. So yeah, this is like a different bands, I think. And this is like a 700 nanometer issue. No, not the one. So time series observation, I think, at different wavelengths has been done, and but actually using one spectrum, you can see that the other teams used this 7DT to observe two asteroids. One is a asteroid without kind of a H2O feature. Another asteroid with a H2O feature. The H2O features occurs at this kind of 700 nanometer width. So it there's a small trough here, and this kind of hydrated asteroids are rare and important tracers of the solar system. So I think that we can, with many 7DS observations, then these hydrated asteroids can be identified, easily. Oops, sorry. So the status of 7DS reference imaging survey, this is kind of a few months old, I think, and then Ji-hoon will probably show you a more updated figure, but it's ongoing. More than 5% have been completed. And then whenever we have a BBH event with a small localization area, relatively close, then we do observations too, so that we can build galaxy catalog there. Galaxy redshift distribution can be done. So hopefully that we can use that for as a dark sirens to do statistical analysis of cosmological parameters. So schedule. So the first step was like performed in 2021 to 23. So construction of the 7DT was performed, and then during the second step, 2024 and 2025, our plan is to complete the 16-unit system by the end of this year. And then maybe if there's enough funding available here and somewhere, then we want to complete the 20 units. and then perform regular 7DS observation, which actually started. And then we are doing the O4B run follow-up observations. So things are going okay. And then the third step will be beyond the 2026. So I hope that beyond 2026, we can continue using this telescope to do maybe more than 7 years, of 7-dimensional sky survey in near future. Almost done. Okay. Outcomes from the subgroup. So this is not very important. Let me speak. But the GW Universe program itself is divided into 2 groups, and our group centered on 7DT. So far published 46 papers, many invited talks, produced 6 PhDs to master's degree students, and then we have studied many topics such as gravitational wave sources, quasars, galaxies, gamma ray bursts, supernova, etc. So I will show you some important results, some of the results that we have done. So scientific results. So one thing is about host galaxy of kilonova. Okay, so when we do the search for kilonova, then we need to cover many areas and many galaxies, and it helps a lot to identify which galaxies are likely to have kilonova. Okay, so galaxies with high kilonova rate should be identified, and typically the stellar mass has been identified as one of the key parameters. But there should be probably other parameters such as star formation rate that could influence the kilonova rate. So what we did is to see what other parameters are important. Okay. So one of the students, Myung Shin, performed this study, and he constructed a volumetric sample of host galaxies of short gamma ray bursts, because the short gamma ray bursts are supposed to be produced by binary neutron star mergers. Okay, and we found the kilonova rate is kind of proportional to both stellar mass and the specific star formation rate, and produced this kind of the equation for the to assign kilonova rate to each galaxy. Okay. And using the kind of prescription, then another student, Ji-Eun performed to construct the sky map of the rate map of the BNS mergers. So to do this, you need to have a stellar mass estimate and also star formation rate estimate. So we examine the galaxy and then WISE data to add the information reliably, and then constructed this kind of map at different distances, so that this can be used for the search for EM counterpart of gravitational wave events, but also we can also target the high rate area to do blind search of kilonova. So also we have done KMT, we have used KMTNet, Korea Microlens Telescope Network, to do follow-up observations of transients and gravitational wave events. KMTNet is a network of 3 1.6 meter telescopes in Southern Hemisphere, South Africa, Australia, and Chile. And nice thing about this telescope is that since these telescopes are located at different longitude, then you can do almost 24 hours coverage of the transient events. And one of the study we had is looked at GRB 223, 03, 078. This is a kind of long gamma ray burst, which are usually believed to be caused by collapse of massive star. But this had an interesting properties that could be associated with kilonova. So we contributed to this effort, published in Nature, for early observation of this event using the KMTNet. Professor Lee mentioned about this event, S24422ED. We also did many observations for other events, but this was supposed to be NSBH event with a 90% localization area of 268 degree, distance of 200 megaparsec. Now I think the terrestrial classification for the terrestrial is 90%, so this may not be the real event, but we did a lot of observations. Interesting thing was that this was actually happened in a low galactic latitude area. So all the groups had a tough time actually to prepare very good reference image and also search for transients because there are too many stars there. Okay, so that kind of emphasized the importance of having galaxy catalog in the low galactic latitude area in advance. We identified tens of candidates in these observations actually using KMTnet data. Also, we did also 7DT data, but they are not being analyzed now. So we did one of the transients looked interesting. So this is the right curve of GW17017 scaled to 200 megaparsec, and GECKO 2024A had a similar kind of behavior in terms of the decay. But later on, we found that this is not decaying like this, and so we found that this is probably not the right transient, right kilonova. But we did a lot of observation. Anyway, in future, the gravitational wave observation horizon will be expand. Right now, I mean, this is the horizon for the BNS merger and then BBH merger. I think it expanded a little bit more. But in future, maybe this will expand to thousands of megaparsec near to the very, very early universe. So in future, there will be hundreds to thousands of BNS mergers or something like that. So it's very, very important to have follow-up facilities ready and kept. So I think that continuing usage of 7DT is very, very important. So anyway, this is last slide, and 7DT is a wide field spectral mapper, and 7DS, the survey with the 7DT has started, and we are making many observations now, and then hopefully next year, maybe we can present more interesting results based on 7DT. Thank you.